In this lesson, we are going to have a short tutorial on glycolysis, which is an energy generating process by which glucose is broken down through a series of metabolic steps to produce pyruvate, ATP, and NADH. So, if you have glucose found in your body, the body makes use of the glucose to produce ATP primarily through glycolysis to produce enough ATP that the body can use for its active example muscle contraction. The body relies on high amount of ATP for usage. Now, for every glucose which goes through glycolytic pathway, it produces a maximum of 4 ATPs, but a net ATP of 2 is generated or what, because there is a consumption of 2 ATPs in the course of the process. 2 NADH are produced in every glycolytic pathway to yield enough ATPs in the electron transport chain. Let's have a pictorial view of how glycolysis proceeds. So let's say you have glucose in your body. The glucose undergo first phosphorylation, and that phosphate comes from ATP to generate ADP by an enzyme called hexokinase. A kinase enzyme do phosphorylation from ATP to form a glucose phosphate. Now the glucose phosphate undergoes further isomerization by phosphoglucoisomers to produce fructose 6-phosphate. So you have glucose from an aldehyde group to a fructose, which is the ketone group. Now the fructose 6-phosphate also undergo a kinase again, undergoes phosphorylation by another ATP to produce fructose 1,6-bisphosphate. So fructose 1,6-bisphosphate has 2 phosphate group, and by the time we get here, we have consumed 2 different ATPs. So here's where the first step and the third step are where ATP is consumed. So when you get a fructose 6-phosphate, and the enzyme which comes to play is aldolase, and the aldolase enzyme is like more of a cleavage enzyme that cleaves the fructose 1,6-bisphosphate with 6 carbons to 2 different 3 carbon art compounds. So we produce dihydroxyacetone phosphates to one side and glyceride 3-phosphate to another side. So the dihydroacetone phosphate undergoes further isomerization to glyceride 3-phosphate. So by the time we get to the 6th step of glycolysis, we might have 3 glyceride 3-phosphate molecules continue the process of glycolysis. So from glyceride 3-phosphate, there's an oxidation reaction which leads to the reduction of NAD plus to NADH. So glyceride 3-phosphate undergoes a phosphorylation to produce 1,3-bisphosphoglycerate. 1,3-bisphosphoglycerate. And this is an oxidation reaction which causes the reduction of NAD plus to NADH. The enzyme here is glyceride 3-phosphate dehydrogenase, which catalyzes an oxidation reaction. So 1,3-bisphosphoglycerate has 2 phosphate groups. The first point of ATP production is conversion of 1,3-bisphosphoglycerate to 3-phosphoglycerate. Here, 1 phosphate molecule is removed from the 1,3-bisphosphoglycerate to ADP to produce ATP. This kind of ATP production is called substrate level phosphorylation because it is just the addition of a phosphate group from a substrate to an ADP to form an ATP. Substrate level phosphorylation. Next, the 3-phosphoglycerate, which is being formed, undergo mutation to form 2-phosphoglycerate, which means that the phosphate on the 3rd carbon is removed to the 2nd carbon of the glycerol. Next, there is a condensation reaction by an enzyme we call the enolase, which causes the release of water to form phosphoenol pyruvate. The phosphoenol pyruvate also has a phosphate group. The second point of ATP production is conversion of phosphoenol pyruvate to pyruvate. Here, the phosphate group is removed from the phosphoenol pyruvate to ADP to produce ATP. This is another type of substrate level phosphorylation. The other type of phosphorylation which occurs in the mitochondria, which we call an oxidative phosphorylation. This is the action of the ATP synthesis in the electron transport chain system, which converts or which produces several molecules of ATP with the use of electron gradient being generated in the inner mitochondrial membrane by the electrons in the NADH, which we call the reducing equivalent. So by the time we get to pyruvate, we might have produced 4 different ATPs, because here this one goes for 2 molecules of glycerol 3-phosphate. So per 1 glucose molecule we produce 4 different ATPs, but we invested 2 ATPs at the beginning, so we produce a net ATP of 2. Let's have a structural view of how it looks like. Have glucose here. The glucose undergoes phosphorylation to glucose 6-phosphate, that is the phosphate on the 6th carbon, then isomerization to fructose 6-phosphate, then phosphorylation again to fructose 1,6-base phosphate. Here's where you have a cleavage. So cleavage into dihydroacetone phosphate and glyceride 3-phosphate. The next is the oxidation to produce 1,3-base phosphoglycerates. The next is substrate level phosphorylation, that is the phosphate group on this carbon is removed to ADP to form ATP through substrate level phosphorylation to produce the first ATP molecule in the glycolytic pathway. Now, by the time we get to 3-phosphoglycerates, there's going to be a mutation by an enzyme phosphoglycerate mutase, which moves the phosphate group on the 3rd carbon to the 2nd carbon to form 2-phosphoglycerate. Next, there's going to be an inhalation, which is the loss of water, to form PEP, which is the phosphoenol pyruvate. The phosphoenol pyruvate further undergoes dephosphorylation or produces 1 ATP by substrate level phosphorylation to produce a pyruvate. That's how glycolysis goes. It produces, 4 different ATPs per 1 molecule of glucose, but a net ATP of 2 is still, because 2 is already invested in the earlier stages of glycolysis. Thanks for watching. Don't forget to subscribe after watching. Thank you.